to recognize the difference between number theory and symbolic representation. Okay, symbolic representation is not quite language, because language has a fixed set of symbols that follow a fixed set of rules that can be applied across other disciplines. Symbolic representation that I'm proposing is not named yet, is for when you are dealing solely with things that you can't calculate. Okay, so in air, light has a refractive index of about 1.003. Okay, so the angle of the total number of angles in a circle times 1.003 d is the diameter of the Earth's atmosphere, and v is a light moving in seconds. Okay, so another thing about symbolic representation. Nothing I do can be nothing I do I am saying as truth right away. I am doing this because I really would like to see what would happen if I did these kinds of things, but I don't have any, like, I can't actually go up to the sun and just like, I mean, like, I don't have any sort of instrument to actually measure the difference between the light that hits the instrument when you're moving very fast. I also can't move very fast, faster than 1,000 miles per hour, for instance, unless you're considering the turn of the Earth, which means I also can't actually go into space, and I can't afford a weather balloon and things like that. And I don't think I would be doing that in the first place anyway. So my exploration in math is more like an art form for me. Where I'm just trying to name things very quickly with letters, because in order to mess around with the numbers to see if I can find any patterns. So now I have to, alright, so now I just did this. Of course, c in the textbook is light, the speed of light. Minus 200, for instance. I couldn't actually put c there, which also means constant, because here it means speed of light, which is a constant, but this is an arbitrary constant, which I just put there because I can't put another symbol there for it. This is one of the problems of the principles of symbolic representation. Now I have to define LDT. It's not very hard. Actually, I think it is very hard to learn calculus without a teacher. But if you can, or if you're advanced enough in like school or what. You can see where I'm going with this thing. Okay, for this is Einstein's work. I would like to refer you to Einstein's theories on the incidence of light, just so you know I'm not pulling this out of my head. because that's what Einstein did, but he was a professional and I am not. Plus. Okay, so this is what Einstein. Wait, did he do this? Yes, he did this. Sorry. Brackets. Equals. Okay. So this is up to the part where Einstein figures out the simple way to put this proportion. So I'm going to go more advanced, and this is alright. This is his famous relativity equation that I am expanding now. Okay, so for those of you who are familiar with calculus, this is the law of cosines. Equals 4i1 squared 4i2 squared plus 8i squared cosine theta 1, 2. Okay, this 1, 2 is just means I1 times I2 and same denominator. Equals 4 over C. So I hope you by now have realized what I am actually trying to find here. Damn it. C. 1. Is it a plus? It's a times. 1, 2, 1 and 2 is squared cosine equals trying to account for time here. Okay, it's been a while since I actually studied this formulation, but I came up with this after the dream I had about the water. Okay. So here so here I was trying to find exactly what the proportion is, not specifically what the value is, but what the proportion is between an object moving at any speed with relation to two incoming lights. So with in proportion to the difference between two incoming light sources. So that there's a difference between one light source for differential value and the other light source differential value. I didn't use much calculus for this actually. If you're one, should I put what theta is? And this is this my final answer? Okay, I challenge you to find what theta is.